Today we are going to study the new chapter from paper 2, that is differentiation. So in that differentiation, let us study what we are going to study in this chapter. So the first topic is derivatives of the composite functions, then geometrical meaning of the derivatives, derivatives of inverse functions, logarithmic differentiation, derivatives of implicit functions, derivatives of parametric functions. So this is the content of this chapter. Now let us recall what we have studied in earlier class, that is in 11th standard. The derivative of f of x with respect to x at x is equal to a. So we are finding the derivative of the function at particular point x is equal to a and is given by f dash at a. It is a notation. F dash means derivative of f. F dash at a is equal to limit of f of a plus h minus f of a upon h as h tends to 0. This is the value of the derivative at point x is equal to a. The derivative can also be defined for f of x. The same derivative can also be defined as at any point x. This is the derivative at particular point x is equal to a. Now I am defining the derivative at any point. That means we are finding the derivative of the function f dash at x is equal to limit of x plus h minus f of x upon h as h tends to 0. This is called the derivative by using the first principle. Derivative using first principle. Now, if the function is given as y is equal to f of x, so f of x is just, we denote it by y, then its derivative is written as dy by dx is equal to f dash of x. Learn this notation, dy by dx is equal to f dash of x. This is the Leibniz notation. For differentiable function y is equal to f of x, if delta x, this is delta x, is a small increment in x. That means there is some increment in the value of x. And how x is increased? It is increased by small value delta x. It is called increment in x. So as x is increased, y must be increased because y is a function of x. So this is the corresponding increment in y is delta y. Then the limit of which? Limit of the incrementary ratio delta y by delta x as delta x tends to 0. This limit exists and is denoted by dy by dx. This is the Leibniz notation of the derivative. Okay. Now, already we have studied the rules of differentiation. If u and v are differentiable functions of x, then y is equal to u plus v, y is equal to u minus v. That means addition of the two functions and subtraction of the two functions. How to take the derivative? There is no problem. Different derivative is the derivative of their addition or derivative of their subtraction. The second rule is y is equal to u into v. It is also called as a product rule. How to find the derivative of product of two functions? We have to keep the first function as it is into derivative of the second function. Then second function as it is into derivative of the first function. This is called product rule. Then we have studied the quotient rule. That means derivative of the quotient of the two functions u by v. It is defined as dy by dx is equal to v into du by dx minus u into dv by dx upon v square. This is the quotient rule. Now let us revise the derivatives of some standard functions that already we have studied. The first one is constant function. The derivative of the constant function is 0. Derivative of the constant function is 0. Derivative of x raised to n, it is a power function. This is a power function, x raised to n. Its derivative is n times x raised to n minus 1. The second one is 1 upon x. 1 upon x, its derivative is minus 1 upon x square. Third, 1 upon x raised to n, its derivative is minus n upon x raised to n minus 1. Now, square root of x, its derivative is 1 upon 2 root x. Sin x derivative cos x. Cos x derivative minus sin x. Then derivative of tan x is sec square x. Derivative of sec x is sec x into tan x. Derivative of cosec x minus cosec x cot x. Derivative of e raised to x is e raised to x. Always keep in your mind, e raised to x, its derivative is itself. Then a raised to x, derivative of a raised to x is a raised to x log x. Then derivative of log x is 1 upon ax. Derivative of x to the base, derivative of log of x to the base a is something different from log x. These two functions are not same. Log of x to the base a, its derivative is given by 1 upon x log a. We have already derived these formulae in 11th standard. So you must recite all the formulae so that you can solve the examples. Now, the next topic is derivatives of composite functions. Now, what is meant by composite functions? So, derivatives of the composite. Composite means function of another function. So, there is a combination of two different functions. So far, we have studied the derivatives of the simple functions like sin x, log x, e raised to x, 2 raised to x, e raised to 3x, and so on. So, but we don't know how to find the derivative of sine of root x, log of sine of x square plus 5, e raised to tan x. Okay, so these are the something complicated functions, and we don't know how to find the derivative of these functions. So these functions are known as composite functions because they are the combination. I know the derivative of sine x, I know the derivative of cos x, but I don't know the derivative of sine root x. So it is a composite functions. So let us study the different composite functions, how to find the derivative of the composite function. So these are the certain examples I have written so that you can understood the what is mean by composite functions. Now you have studied x raised to 4, but you don't have studied cos raised to 4x. You studied log x, but you have not studied log of sin x. Okay, so these are all composite functions. Tan x raised to sin x, cos of log x, tan of e raised to x. These are all composite functions. And we have to study how to find derivatives of the composite functions. For that, we will study one theorem. What is that theorem? If y is equal to f of u is a differentiable function of u, and u is equal to g of x is a differentiable function of x, such that the composite function y is equal to f of g of x. This is a composite function. F of g of x is a differentiable function of x, and its derivative is given by dy by dx. So we are differentiating y with respect to x is given by dy by du into du by dx. That means we are not going to differentiate y with respect to x directly. We are differentiating y first of all with respect to u, and then that u with respect to x. This formula is known as chain rule. What is known as chain rule? Now, given that y is equal to f of u and u is equal to g of x. Now, we assume that u is not a constant function. Okay, u is not a constant function. So let there be a small increment in the value of x, delta x. Let delta x be the small increment in x. Then as u is a function of x and there is increment in x, so u must be increased. and let delta u and delta y be the corresponding increments in u and y respectively. Why there are increments in u and y? Because y is a function of u is a function of x, and there is increment in x. So due to increment in x, there will be increment in u, and due to increment in u, there will be increment in y. As delta x, delta u, delta y are small increments in x, u and y. Okay, so respectively, such that delta x is not equal to 0, delta u is not equal to 0, and delta y is not equal to 0. Then we consider the incrementary ratio delta y by delta x is equal to, or this can be written as delta y by delta u into delta u by delta x, so that they can cancel and we will get the same incrementary ratio. Now, taking limit as delta x tends to 0 on both the sides. Now we will take the limit on both the sides as limit delta x tends to 0. Then what we get? As delta x tends to 0, delta u tends to 0. Why it happens? Because u is function of x. Whatever the value of x will change, that will affect the function u. As delta x tends to 0, the increment is tending to 0. So whatever the increment we got in u, that also goes to 0. So I can write the given equation as, instead of delta x tends to 0, I replaced here delta u tends to 0. Now in the theorem, it is given that y is a differentiable function of u and u is a differentiable function of x. That means we can find derivative of y with respect to u and derivative of u with respect to x. This is our equation number 2. Why we write this? Because of this statement, y is a differentiable function of u and u is differentiable function of x. So from 1 and 2, so we will put this equation 2 in this equation first. We get limit delta y by delta x as delta x tends to 0 is equal to dy by du into du by dx. Equation number 3. Now from this equation, it is we can say that the right hand side exists. Right hand side exists and is finite. So that must implies that left hand side must exist. Okay, and that must exist and also finite. So we must have, by Leibniz notation, limit of delta y by delta x as delta x tends to 0 must be equal to dy by dx. Then equation 3 becomes, so we will put this value in equation 3. Dy by dx is equal to dy by du into du by dx. So this is the chain rule we are using to find the derivatives of the composite function, and this theorem may ask for the bold for 4 marks. Many times these theorems were asked by bold for 4 marks. So keep studying this theorem and practice it. Let us study the notes on this theorem. The derivative of the composite function can also be expressed as follows. Y is equal to f of u is a differentiable function of u, and u is equal to g of x is a differentiable function of x, such that the composite function y is equal to f of g of x is defined as dy by dx is equal to f dash of g of x into g dash of x. If y is equal to f of v is a differentiable function of v, and v is equal to g of u is a differentiable function of u, and u is equal to h of x is a differentiable function of x, that means we are going deeper and deeper. Initially y is function of only u and u is a function of x. Here y is function of u, v is function of u, and u is function of x. So there is a chain. Okay, so we cannot directly differentiate y with respect to x. So we have to differentiate y with respect to v, then v with respect to u, and then u with respect to x. The third node is saying that we can continuing this differentiation for many n differentiable functions. Ui plus 1, I is equal to 1 to up to n. They are all differentiable functions of it. So dy by dx is dy by du1. So derivative of y with respect to u1, derivative of u1 with respect to u2, derivative of u2 with respect to u3, derivative of un minus 1 with respect to un, derivative of un with respect to x. So this is just like a chain, and that's why we call it as a chain rule. Now, derivatives of some standard composite functions. Now we will look or study derivatives of standard composite functions so that we can use them in solving the examples. Look at the first table. Here, our base function is f of x. Here, whatever I have written, f of x, that f of x may be sin x, that f of x may be cos x, that f of x may be e raised to x, that f of x may be log x, that f of x may be tan of x, any function that you have studied as a simple function whose derivative you have studied, you know. Okay, so f of x raised to n, its derivative is given by n times f of x raised to n minus 1 f dash of x. Now, how it comes, I will show you for this. What they are given? I will say y is equal to f of x bracket raised to n. So what in next step I will say that it is nothing but u is equal to u raised to n. And what is u? U is equal to f of x. Okay. So now here y becomes a function of u. So here I will find dy by du, derivative of y with respect to u. Now it is a power function, simple function, x raised to n. Its derivative is n times u raised to n minus 1. And here derivative of u, as f of x is a differential function, derivative of u with respect to x is nothing but f dash of x. So what is the chain rule? What chain rule tells us? So dy by dx is equal to this into this. So n times u raised to n minus 1 into f dash of x. But what is u? U is f of x. So you got n times f of x raised to n minus 1 into f dash of x. By this way, you can prove all these formulae. Okay. So f of x raised to n, its derivative is given by n times f of x raised to n minus 1 into f dash of x. Root of f of x is given by 1 upon 2 root f of x into f dash of x. 1 upon f of x raised to n, its derivative is given by minus n times f dash of x upon f of x raised to n plus 1. Sin of f of x, its derivative is given by cos f of x into f dash of x. Cos f of x, its derivative is given by derivative of cos of f of x is cos f of x into f dash of x. Derivative of tan of f of x is sec square f of x into f dash of x. Derivative of cot of f of x is minus cosec square f of x into f dash of x. Look at the next table. Derivative of cot of f of x is minus cosec square f of x into f dash of x. Derivative of sec f of x is sec f of x into tan f of x into f dash of x. Derivative of cosec f of x is minus cosec f of x into cot f of x into f dash of x. Now, a raised to f of x, its derivative is given by a raised to f of x into log a into f dash of x. E raised to f of x, its derivative is given by e raised to f of x into f dash of x. Log of f of x, its derivative is f dash of x upon f of x. Log of f of x to the base a is f dash of x upon log of a into f of x. So these are certain derivatives of some standard uh, composite functions. Okay.